Okay. Well, this is a little weird, probably weirder for you than me, but Nico asked me to give you a review of the work I've been doing recently and in the past. That's who I am. That's where I've been recently. So what I'm going to try and do is give you a very quick run through stellar evolution, because I'm assured that most of you have no real knowledge of that. Talk about the Edinburgh-Cape Blue Object Survey, which occupied me and a number of other people for many years, and then some of the results from that. I want to talk about particularly the hot subdwarf stars, and I'll explain what they are. And if I have time, the helium stars. I did do a real-time run through this, and if I talk very quickly, I can do everything, but invariably I'll probably run short. So one of the, oh dear, that's not quite in focus. Is there a, can you see that okay? I don't know if there's a, is there a way of focusing this thing? Well, anyway, this is a so-called Hertzsprung-Russell diagram. I seem to have lost the pointer. Oh no, there it is. Okay, so what this is a plot of, can't see the damn thing. Okay, this is it's a plot of stellar luminosity. So here's luminosity from about 1 million times the solar luminosity to about 1/1,000,000th of the solar luminosity. And here's temperature from about 2000 degrees to about 100,000 degrees. And what you see in this diagram is stars. This star's plotted from the Hipparcos satellite, which went up about 10 years ago or so and measured hundreds of thousands of stars. And what you see is, this is called the main sequence. Also, we call that dwarf stars. This is where stars are when they start burning hydrogen. Sorry, in astronomy, we say burn when we mean fuse. I don't know where that came from. I don't know if you do the same thing in nuclear physics, but when we say hydrogen burning, we mean hydrogen burning to helium. So stars in this region are burning hydrogen to helium, and those we call dwarfs. They're giants because they're much more luminous, and supergiants. And you can see that various areas of the diagram are not well populated, and that's usually because stellar evolution through those areas is very fast. And on the main sequence, the dwarf stars, it's a mass sequence. So it goes from about 100 times the solar mass up here to about 1/12 of the solar mass down at the bottom. And the more massive a star is, the hotter it is inside, the faster the nuclear reactions go. So that lifetimes on the main sequence, before main sequence stars start to evolve away, are typically, say, 1 million years. Up there, for the sun, about 10 billion years. And for the red dwarf stars down here, trillions of years. So when a star arrives on the main sequence, it's fusing hydrogen, it's burning hydrogen to helium in the center. I'm not going to try and tell you guys about the proton-proton chain. And that's more or less what a star like the sun would look like. Hotter stars would have more radiative, the radiative zones would be bigger, cooler stars, convective, would be bigger. So a star like that on the main sequence, like the sun, slowly builds up a helium core as the hydrogen is burnt to helium. And then what happens after time is the core is essentially doing nothing. It's inert. It is in fact electron degenerate. And there's a hydrogen burning shell around that, which slowly moves outwards as the helium core builds up. As that happens, after, in the case of the sun, about 10 billion years, it starts to push the outer layers out. The star becomes much bigger and therefore more luminous, and much cooler and therefore redder. So it moves into what we call the red giant branch. And then eventually, the core can, there's no, as this burning layer moves out, there's less and less nuclear reactions. Eventually it stops. The star starts to contract, and that heats up the center. And in the case of a star like the sun, eventually it will get hot enough to start fusing helium, to start burning helium into heavier elements. And then what happens then is the sun comes from the red giant branch onto what we call the horizontal branch. And it's then in a stage where it's got helium burning in the core to carbon, mainly to carbon and oxygen. There's a helium burning shell around that, and there's a hydrogen burning shell if the center is hot enough. So the star sits on the horizontal branch for a while, and then Eventually, the same process happens. The core becomes isothermal, becomes degenerate, or still is degenerate, I should say, and the star becomes an asymptotic giant. It's so called because it sort of asymptotically, and I'll show you a picture in a minute, moves towards the red giant branch. Then for a star like the sun, it doesn't, when that process stops and it starts to contract, it never gets hot enough to burn heavier elements than carbon. So the star then lives on gravity. The star shrinks, gets hotter and hotter and hotter, moves across this diagram, and eventually ends up on the white dwarf sequence, where effectively it's lost the outer layers because there's a lot of mass loss at the top of the red giant branch and the asymptotic giant branch. And what you're left with is the carbon oxygen core, in that case, of the red, what was the red giant, and that becomes a white dwarf, and it just cools off. And that takes forever. I mean, many times the age of the universe. And we can see actually this, oh, sorry, this is just to give you some idea of timescale. So typically about 10 billion years for a star like the sun on the main sequence, about 1 billion years in the red giant region, 100 million years on the horizontal branch, and 1 million years asymptotic giant branch. And this goes very quickly in a few thousand years. And then, as I say, white dwarf cooling goes on for a long time. So this is in the satellite to our own galaxy. There are dozens of these globular clusters, 100,000 stars. And if you make effectively a Hertzsprung-Russell diagram, it's now turned into a color magnitude. So this is actually its absolute magnitude, but it's simply a measure of luminosity again, with the most luminous stars at the top. And this is a color, the difference between two filters. If you measure stars with two different filters, you get a measure of the color. So it's hotter this way, more luminous that way. And it's just an HR diagram, effectively. So here you see the main sequence. A star like the sun, which would be about here, you can see the main sequence would go up like this. It's already beginning to evolve away from the main sequence. So this cluster of stars, actually, this is a composite diagram, but that cluster of stars will be at least 10 billion years old. Here's the giant branch. You don't really see the asymptotic giant branch. Here's the horizontal branch. And then down here are the stars I'm particularly interested in, sometimes referred to as the vertical branch because it's horizontal and vertical. So these are stars that are now burning helium in the core. And up here, I'm also interested in some stars, but you can see there's nothing much up here. The stars evolve very quickly through that phase until they get to the white dwarf cooling section. And many years ago, it was obvious that the stars we and myself and a few other people in Cape Town and other parts of the southern hemisphere were interested in were the white dwarfs and the hot subdwarfs, these very evolved stars. But it turns out that nearly all the stars known in these classes were in the northern hemisphere. And the reason for that is very simple. That's where all the observatories were until fairly recently, until about 50 years ago. So a lot of the surveys had been done in the north, and we were very keen to get something, to find new targets to look at in the south. So we started this Edinburgh-Cape survey. It was started really by Brian Warner. I was trying to do something. I was looking at experimenting with how I could do something in the south, and I realized other people were doing it, and we joined together. Dara was one of Brian's students. He was at UCT for a while and then went to SAAO. Chris Kuhn was at SAAO and moved here. Bob Stobie was at Royal Observatory Edinburgh and eventually became director of SAAO. So these people at the bottom were involved because at that time, Royal Observatory Edinburgh was responsible for the Anglo-Australian Schmidt telescope. And they could do and had done large-scale surveys in the south. So these people were mostly involved, but there were many, many other people involved in this. And so the original plan went something like this. This is the southern hemisphere just plotted schematically. So there's been no attempt to compensate for the projection. So all of these represent Schmidt fields. Schmidt is a special kind of telescope for doing wide angle photography. And so all these fields are actually square and the same size, but it's just the fact that it's schematic. So this represents the southern hemisphere. The galactic the galactic plane runs around here, and we wanted to avoid that because the star densities are very high and they're mostly normal stars. And so we were looking at the south galactic cap, which is this area here, and a bit of the north galactic cap that sticks down from the northern hemisphere. We were originally going to do these zones in here, but we found they'd already been done from the north. So the idea was, I can explain later if you want, use photography, but we used photographic plates. They would be about this sort of size on a Schmidt telescope, and they would get you something over 5 degrees square on the sky, which is, if you hold up 3 fingers, that's about 5 degrees on the sky. And so it takes about 900 of those plates of those areas to cover the whole hemisphere. And we took plates in 2 colors, blue and ultraviolet. Of course, in ultraviolet in astronomy is really the very, very near ultraviolet, because the atmosphere chops off everything below about 3,500 angstroms. No, sorry, 350 nanometers, 360 nanometers, something like that. So these plates were taken, long exposures, because the quantum efficiency of plates in the ultraviolet is very, very low. And this magnitude, I'll explain about magnitudes in a minute. So we took these plates, they were measured with Cosmos and supercosmos at the Royal Observatory, Edinburgh. These would measure maybe 100,000 or 200,000 stars on a plate in a few hours, and give you the magnitudes and other information. So I couldn't find a picture of the original data, but this is typically what we would get from a Schmidt plate. All these little crosses are stars, objects that haven't been looked at. And you have to imagine that this whole area here would be completely solid with crosses. So what we did was we set a magnitude cutoff. This is apparent brightness. So 16.5 magnitudes, that's about 10,000 times fainter than the faintest star you could see in the sky with your naked eye on a dark site, not from Cape Town. And so we started observing the stars which were bluest and moving this way until we reached, what are these black dots? We started to pick up normal stars, much like the sun, but with they come into this plot because they are very weak in metals. And I should say that astronomers call everything that isn't hydrogen and helium a metal. So everything else is a metal, including lithium and beryllium. And these stars, they're very weak in metals, so the ultraviolet is enhanced relative to a star like the sun. So as soon as we started picking up those stars, we stopped. And so we would pick up, I think these triangles are hot subdwarfs. The circles, I think, are hot white dwarfs. And I think the squares were emission line galaxies, for example. And we would do this for something round about, I think we got this about in the, oh, did I just do? Oh no, there we go. I've skipped one. I've lost a frame. Oh, well, never mind. It was just a frame that showed we didn't quite complete the survey, and I was going to give you my excuses for that. So having found these stars from color plots of taken from this survey, we used the South African Astronomical Observatory's 1.9 meter and 1 meter telescopes to do follow-up spectroscopy and photometry. So for example, these are low dispersion spectrograms. This is a subdwarf. You can see the Balmer series of hydrogen there, and it's hot. That's helium-1 there, 4471. And you only see the Balmer series to about n equals 10 or 11 because Stark effect broadens the line so much. These are higher gravity stars than stars like the sun, that the lines just merge and you can't detect them. This is a lower gravity star, and you can see the Balmer series. Well, you can't, but take my word for it, to about n equals 14. It's a lower gravity star. This is just one of these normal F stars, not normal, but metal weak F stars. You can see the calcium-2 lines. And this is a color plot. So you've got temperature going this way, temperature going that way. So these are the hot stars, these are the cooler stars. And on this diagram, this is where stars lie. And that's because Balmer series absorption for stars takes away a lot of the ultraviolet, or some of the ultraviolet light, and you get this dip. This is what a black body would look like on this plot. These stars, or objects up here typically show strong emission lines, and that's why their colors look hotter than a black body. And they included things like cataclysmic variables and white dwarf stars. Cataclysmic variables, which are white dwarfs in binary systems, and emission line galaxies. But we were typically interested in stars like these, the hot subdwarfs and the white dwarfs. Oh, no, there it is. Sorry, I don't know what I did there. That was the actual survey as completed. We actually, Edinburgh, the Anglo-Australian Schmidt took all of these plates. We got all of the fields taken. And by the time this survey was getting on towards the end, photography had stopped. People were using electronic detectors. And the UK decided to close down its wide field astronomy program. And they said, we will measure all the plates before we close it down. And they didn't. Oh, gone again. Nevertheless, we still found about something over 2,000 new objects which had not previously been known to be very hot and evolved. So that's what we were looking for. While this survey was all going on, of course, which was extremely tedious, I have to tell you in observational terms, we were beginning to look at the individual objects. One of the things we were particularly interested to find was new pulsating white dwarfs. And this star, I should not apologize, but one of the things about astronomy is the nomenclature is awful. Everybody makes up their own nomenclature. These were stars found in the EC survey. And these are the sort of on the sky equivalents of longitude and latitude. That's a common way of doing it. Even the Gaia satellite uses this, except they have about 20 digits, which makes it absolutely impossible to remember any star's name at all. But we thought this was, we actually classified it wrongly. It got onto our white dwarf list. And now this is what we call a light curve, even though it's flat. This is light, this is time, reading like a book, and this is brightness. So up is brighter, down is fainter. And so this reads like this, and it's 0.1, that's 0.01 of a day. So that's a bit over an hour of a light curve. And you'd look at that and you'd think, that's just random. There's no signal in there at all. When you do the Fourier transform, there's a signal here at about 140 seconds. And we'd misclassified the star. The guy who'd observed it said it was just on the list, so he didn't question it and observed it. And he looked at that and said, no, there's nothing there. Fortunately, somebody was checking, and somebody was doing a Fourier transform of all the data that was coming out. It was actually Bob, I think, Bob Stobie, and he said, oh, this looks like a real signal. The low frequency stuff is to do with the sky, or at least you can't separate the sky from real signal. So we ignore that. He said, this looks real. And we said, no, that can't be right, because when he found it, we had a look and we said, but it's not a white dwarf. So we went and re-observed it, and these are different nights. And right enough, you can see there's this one, I think it's about 144 seconds. And there's something here as well, which you can see. And this was the first known hot subdwarf pulsator. And then we got very excited, of course. This even made the local papers. I was both surprised and embarrassed. One thing you can see here is this was a short run. You can see from the width of the Fourier peak there. Once we discovered and decided that it was real, we started doing longer exposures. So of course the peak gets much narrower and the frequency gets better defined. So then we started looking for other stars like this. We kind of then went, we're not interested in white dwarfs anymore. We want to find more of these. So this is another one, again, a telephone number. But now you can see this is about half an hour along here. So that's 3 hours. You can see now there's a very definite variation. You can see it with the eye. And when you do the Fourier analysis, you get something like this. So these peaks run from about, well, this is microhertz. So it's from about, what would it be, about 100 seconds down to about 200 seconds, something like that, something in that bracket. Most of these stars are in that sort of range, 2 to 3 minutes typically, perhaps a bit more. This is just the window function. You're okay. Nico told me you've studied Fourier transforms, so you're okay with the window function. Yeah. Well, anyway, the window function is you can see here, it's a continuous stream of data. This is the sync function that's just to do with the fact that you've got a finite string of data, and you can see again this peak's much narrower than that one, which is because this data set must have been longer than that one. And now when you start finding more frequencies there, then you might well have asked the question, why do you want to know all this stuff? There is then the possibility and the more frequencies the better, that you can match these observed frequencies with models of what we think a subdwarf star looks like. And then you do the iteration where you can work backwards and forwards between models and observations. And if you improve these things and get really good, you can do things like get the pulsation mass of the star. You can, in fact, not easy with data, you can't do it with data like this, but satellite data, the Kepler satellite ran for 4 years on a patch of the northern sky and included some of these stars, and they're able to do things like infer that the star was rotating differentially. The inside of the star was rotating faster than the outside, much like the sun. And that there may be layers that you get pulsation modes that are trapped and bounce between, say, a core. And we started calling this asteroseismology because it's just like seismology on Earth, except that you can't put detectors all over the star. All you get is the integrated light because the star is a point source. But the pulsations are very, very important. I'll try and touch on 1 or 2 areas where they're useful in a different way. And then as we found more of these things, this one you can see, it looks like a textbook case of beating, and the Fourier transform tells you that's exactly what it is. However, if you now look, these are three nights in 1 week of observing. The right-hand peak is gone, it comes back, another peak appears, and then a couple of months later, the left-hand peak is gone. And it stays gone, and the others tend to fade out. And your first thought is, well, okay, we've only got short trains of data, so the resolution of the frequency is not good. It's a few microhertz. It could simply be that there are 2 frequencies very close together that beat, and that makes the overall frequency that you do not resolve look like it's coming and going. And then we found a star, this star, well, and others like it. This is early data that we took. You can see this thing appears. And then this is much later data. Now, observing the way we do from the ground, we don't get very good sampling. But this frequency marked with a star here and that one, they both appeared in the data and had not been seen before, and then disappeared and never appeared again, as far as we can tell. So something more than simple frequency. It may be there are many, many frequencies in there, and then we're never going to resolve them. But it may be something like energy is somehow shifting around between the modes of pulsation in the star, and we don't understand that. We don't fully understand it. There are suggestions. Okay, well, that's the one, probably the biggest thing that came out of the survey. Before the survey started, I found this star, which was the first eclipsing sdB star known. And eclipsing stars are particularly important because if you look at this light curve, so it's the same thing. This is brighter, this is fainter. There's a hot star and a cool star. When the cool star comes in front of the hot star, you get an eclipse, and then vice versa, the hot star goes in front of the cool star, you get a smaller eclipse. And if you've got an eclipsing binary, and you know that the plane of the orbit is more or less in the line of sight, so you don't have inclination problems, sin I. This distance here in time between there and there, or here and here, is the size of the smaller star, the radius of the smaller star as it goes behind the bigger one. This distance between here and there, or there and there, is the radius of the bigger one. Relative to the orbit, the separation. And we know the period of the star, we know what that is. Because the orbit is in the plane of sight, if we measure the velocity, the peak velocities tell you the speed the star's traveling in the orbit. So you can get the size of the actual radius of the stars. And if you've got both sets of spectral lines, you can measure them, then Kepler's law gives you the absolute sizes, masses of the stars. So from a binary system, we can in principle get absolute values for the parameters, which is quite important because we have no other way of directly measuring the mass of a star, really. In the case of this star, we only see one set of spectral lines. Actually, that's not quite true. Many years after this work was done, some very clever work detected the second set. They're very, very faint. And so what we did was we assumed that the mass of the primary, the subdwarf, was half a solar mass, and that makes the mass of the secondary about somewhat less than a tenth. That's right on the edge of whether it's a star or not. If it was less massive than that, then nuclear reactions never start in the center, and the protostar just cools off. So we can actually get information, direct information on the parameters of stars. And that also then feeds back into your evolution models. I think that's everything I wanted to say there. So this is just a model of the system. This is what the velocity, the most massive star has got the smaller velocity. It's not calibrated. But I put this picture up just to show you another factor, which is the one star. Sorry, I've just colored in a printout of the model. The one star is very hot, the other star is very cool. But because they're so close together, these stars are about a tenth of the solar radius each, and they're separated by about the solar radius, or a bit more than that. Because these stars are so close, there's a hot spot that we call it a reflection effect, and that's what you see here. As the cool star comes out from in front of the hot star and goes round the back, you start to see more and more of that hot spot, and then it's eclipsed. And in fact, you can say with a system like this, the hot star isn't eclipsing the cool star, it's really just eclipsing the hot spot. It's eclipsing itself, in effect. But that explains the shape of these curves. And this star was an attempt to model the second. This was discovered by Fred Morang, also at Sutherland site. And there's the same parameters, slightly different values for radius and temperature, but you can get the absolute parameters out of the system, out of these observations, plus the velocities. Well, every once in a while, not very often, you get the feeling that all your birthdays have come at once. And that's what we got when we discovered this star. So this is a pulsating star. You can see the eclipses, you can see the reflection effect. Sorry, it's an eclipsing. It's also pulsating, and you can even see that it's beating. The pulsations come and go to some extent. Now, this is a kind of, when we found this, it was described by somebody as a Rosetta Stone. I'll explain why in a minute. This is just an expansion of the thing. So you can see it's pulsating there. This is the Fourier transform of one night. I think that's just another night. So you can see there's a couple of frequencies there. When you get something really interesting like this, it's quite good to be able to do the whole telescope campaign. So this is where we get a bunch of observatories linked together. And typically, but not always, an object is picked that's somewhere near the equator so that it can be seen from both north and south. And then you can observe the star. These campaigns run for about 2 weeks. You can observe the star as it sets in Australia. You can pick it up here, and you've got some capability north and south. If one site is cloudy, you'd hope to be able to get it from another site. And this is the sort of data we get from that. Instead of this being from a few hours data, we've now got 2 weeks of data. You can actually see that this frequency isn't there. And this frequency here is not that one, it's that one, I think. Same with that. But now, instead of 2 frequencies, or maybe a few more than 2 frequencies, with a whole Earth telescope campaign, you can get, I think in this case, we got up to about 30 frequencies. So, and there's an example of, even though we had something like a dozen observatories on different sites, north and south, there are still big gaps in the data because it's intensely infuriating when all the observatories, thousands of kilometers apart and in different hemispheres, are all clouded out. But nonetheless, you can still get, this is just the first half of the data and the second half of the data. And this is an attempt to model these frequencies by having model stars of a range of temperatures, gravities, masses, and so on, and just computing those, what the pulsations would look like until you get something that matches. And as I say, you have then an iterative feedback between model and observations. The reason why that campaign was done, because these pulsations are not radial pulsations. It's not the star getting bigger and smaller. They're spherical harmonics, and I think you do spherical harmonics in nuclear physics. You're perfectly familiar with all that sort of thing. So if you have a star that's pulsating with bits of the star getting hotter and cooler, bits of the star moving out, bits of the star moving in, what you do when you observe that star is you integrate all those together, because a star is a point source to us. And you can't really separate those. If, however, you've got a star being eclipsed, you're covering up the star in different ways. And this was some work done by Mike Reed for his thesis. And he calculated what various modes would look like as you go through eclipse. So modes that you can't see because they average out can suddenly appear and change shape and do different things. So that campaign was done to try and actually identify pulsation modes on the stars by using the eclipses. It didn't work. It didn't work because the eclipse time is so short compared to the total light time. We couldn't get enough data. Well, I say we as if I did it. Mike Reed could not get enough data, but he still got his PhD. Okay, so that was a moment of great excitement, which didn't make the newspapers and nobody cared, but we all thought it was great. O-C diagrams. This is probably just an astronomy thing. Does everybody know what that is or not? No? No? Okay. It's extremely simple. If you have some event like an eclipse or a pulsation that you measure 1, 2, 3, that's the period. You've got the period and you measure it over here and you get n. You can just write that the event, eclipse or whatever it is sometime t0 there, plus n times the period. So you then have an ephemeris which predicts when all the eclipses will happen. Now, if you go on, you don't observe the star for a long time, and you go back and observe it again, say the next year, and then you plot the difference O minus C between your ephemeris and when the observation happens. So you have discovery observations, and you find that it's drifting. That means you've got the period slightly wrong. So you can just adjust the period and then everything falls into line. If, however, you've got something that looks like this, it means the period is decreasing. It's just an easy way of displaying the observational data. So this was that star that I just showed you, this one. We'd measured eclipses, got the timings to as best we could, a few seconds. And then if you plot, this was the data from 4 seasons. So you can see it looks flat. These were just, I put those in just to show what certain pulsation period changes would look like, decrease or increase. But then after a few more years, it starts to do that. So the period's decreasing. Okay, I've got some more data. Now, you look at this, your first thought is, well, it didn't your first thought because I knew it didn't work, but you might think gravitational radiation, that would be natural. The binary it's a very close binary system, you would expect gravitational radiation losses. We can't measure them on this timescale, they're too small. But it turns out that I didn't have time to do the plot. I have more data which shows this curves up. And when you see a sinusoid like that, your immediate thought in a binary system, well, the binary is doing this, but it's also orbiting another star. So you will have a time lag as the binary goes around the orbit of the other star. And that a sinusoid would be explainable as a triple system, a close binary and another one. And there have been all kinds of attempts to do this, because since we found these first systems, since we found the period changes, a lot of people have been looking at this. This, however, is that second star I showed you, HW Ver, the one that Fred discovered. So this is now the O-C period over something like, 30 years? No, more than that. These were Fred's first observations. I started picking up on it. The red data is all SAO data. This is kept from the Kepler satellite, and there are a few other things in there. And the temptation is, I know this guy Lee and his group, they are the purple observations. They got observations to here, and then fitted this O-C curve with a quadratic drift, which they didn't explain, and 2 planets. But every time you put a planet into a system, you add in 4 or 5 new parameters. And if you put 2 planets in, you've added in 10 new parameters. You can fit anything. And by the time they published this wonderful fit to the data, I'd already got those data, and I knew it was wrong. And this was another attempt to do it by people who had data up to there, and it was wrong. And I don't know how to explain that. You could say, yeah, we can. You can't rule out the fact that there is a binary system with planets. But if you start putting in more and more planets, I mean, you know what Fourier analysis, you can make a square wave if you have enough sine waves. You can fit anything if you've got enough parameters. And we don't know what this is. It's not, there might be planets there might be other objects there, but we don't know what they are. And we don't know what, I mean, it almost looks like a damped oscillation, but there's no explanation for that in a binary system. We've been looking at, some friends of mine have been looking at whether you can exchange mass or lose mass. But for these stars, they're well separated. There's no indication that they're losing or gaining mass at all. So we don't know what that is. We have no idea what causes that. Okay, right. Have I got another few minutes left? Can I just go on for a bit longer? Sorry? Yes. Okay. So that was basically the subdwarfs. We looked at binaries, tried to explain to you how pulsating stars and binaries both contribute to our knowledge of the basic parameters of stars, and that ties into the modeling of stars. It's very difficult because, for example, at the top of the red giant branch, there's mass loss because the outer envelope is like a good vacuum. And the surface gravity is very low, so it's very easy for material to escape. The stellar winds, there's a lot of mass loss, but we don't know exactly what it is, and you can make models with any amount of mass loss, but again, you've got truckloads of parameters, or at least one parameter that's almost infinitely variable. Now, just talk about the helium stars. These are stars that now we thought for a long time were post the asymptotic giant branch. So they've been through hydrogen burning, they've been through helium burning, they've become a red giant, they've become an asymptotic red giant branch, and now they're traveling quickly to not moving anywhere, but they're getting very much hotter and very much fainter fairly quickly. And the reason why these came onto the radar is that they are literally helium stars. Their outer atmospheres even show, for most of them, almost no hydrogen at all, which is crazy in a universe that's 90% hydrogen. Even very evolved stars have mostly hydrogen atmospheres. This particular star has got about 1% hydrogen. The other stars in this group, it's 0.000 something percent hydrogen. They are often called extreme helium stars or extremely hydrogen deficient stars. And these are a couple of light curves I got from SAO about 10 years apart. So again, this is bright up, faint down. Now, these stars are not, these stars are much simpler. They are radially pulsating, and they are radially pulsating in the fundamental mode. So that makes them much simpler to deal with. The reason, this is the period, the reason why there's a double bump is that as the star expands and contracts, it gets hotter and cooler. So here it's smaller but hotter, and here it's bigger but cooler. So you get effectively a bump because of the temperature change, and another bump because of the radius change. Of course, both of those things are going on all the time at the same time because the star's doing this. So they were taken 10 years apart to all intents and purposes. There's no change at all in that light curve. The variation was discovered by Arlo Landolt in America in about the mid-70s. And when I moved to this country in late 1980, in those days, cover your ears, youngsters, there were no such things as laptops. We didn't have personal computers. There wasn't an internet. We didn't have email. All my stuff was in a ship somewhere being shipped to South Africa. I had nothing to do, and I got observing time. So I thought, I'll observe this star again. So I did. I got a couple of light curves, and a friend of mine, a guy I was a grad student with, Tony Linus Gray, who is now also an honorary professor at UWC and UCL and Oxford. But I wrote to him a letter, and 2 weeks later got a reply. I said, I can't fit my observations with Arlo Landolt's observations. They don't, the O-Cs don't fit properly. I'd got observations over, I don't know, a few nights spread over a few months. And Tony said, well, I've got some data from the year before, 2 years before. He said, I'll send it to you. And a week later it arrived. And we patched that together and we found this. So now the period is changing. But now this is a pulsating star. It's not an eclipsing star. As far as we know, it's not in a binary system of any kind. And I carried on observing it. And then there's something like, I don't know, 40 or so years of observation. So this is the quadratic term. This is just if you take a linear O-C. This diagram here is the same thing. It's just taking little bits of data spread over a year or 2 years and calculating what I call the instantaneous period. And that's a straight line fit to it. You can see it's not a perfect fit. It's up here, there, and down. But the gradient of this agrees with the gradient you get from that. And that's good because when we published the first paper using data between here and here, the first thing I saw you, we dropped a cycle. We just didn't know. When n is very large, n is nearly the same as n-1 and n+1. But with more data, we got that right. And if you fit now a quadratic to it, these are the residuals. If you fit a quartic to it, these are the residuals. So there's stuff going on there. Of course, what we're doing here is representing some physical thing with polynomials, which may not mean anything. It's just a representation. But if you think about it, if the star is, I think I got a slide for, yeah, pulsation theory gives you p root, mean density of the star is constant. So that's true. So if the period's decreasing and nothing else is going on, the star, either the mass of the star is increasing, which is unlikely because we don't see any evidence for that, or the radius of the star is decreasing. And this, I get very excited about this for no real reason, except the fact that it's amazing to me that you can look at a physical process in a star, which normally would take place over very large time frames, and you can see the star is changing. And if you try and do some sums about, let's say, how much would the temperature change of the star if the radius is decreasing by the amount that this suggests? And it comes to about 1 degree a year, which is, you can't measure that. In that time scale, the star's temperature would have changed by about 30 or 40 degrees, which is not measurable. We can't measure that sensibly. We can't measure the radius change. It's impossible. So, but by measuring the pulsations and the rate at which they change, we can get information on stellar evolution. And if you think about it, you have a star which is now, we originally thought, post-asymptotic giant branch. So it's a helium, it's a carbon-oxygen core with a helium shell and virtually no hydrogen at all. And all it's doing is contracting, but it's pulsating. So that you would expect from that, if the star is contracting and getting smaller, the mean density is going up, the star will pulsate faster. As it contracts, however, the star is getting denser and denser, and the rate of contraction will slow down. So these do really show that it is related to physics. There was, this is a very old model by Detlef Schoenbrunner. And what he did was just take a star like I've just described to you and say, what happens if we just let this evolve? We let it contract, and this is what it does. It goes from very hot, very large, to being very small, very bright, and then it's white dwarf cooling. But here you can see these are about, on that scale, for a 0.7 solar mass star. This is only 1,000 years, each of them. So it's a few thousands of years. It's a very fast phase of evolution. But there are now more modern models which actually still agree with slightly different numbers, but they still agree with the idea that this is a star that's shrinking. Yeah, I can explain. This is just it's kind of an HR diagram, but it's a stability plot. So these are hydrogen deficient stars. These regions here are completely stable against pulsation. So you don't get pulsation here. This region here is unstable to pulsation. And these stars are very large. They're much larger than the one I've just shown you. And they do vary, but the varying is, yeah, I'm nearly there. The varying is very sloppy. We don't see any coherent periods. The periods are very long, many days, weeks, months. But this finger of instability down here, where the stars can pulsate, that's the star I've just showed you. And this was another star, which was not known to pulsate, in more or less the same area. Chris Kuhn and I looked at it. This was the first data we took, which was photomultiplier data. But you can see there's and then we got CCDs arrived, charge coupled devices, and we can see a much better light curve. So this is just the two stars compared. The period's almost exactly the same, 1/10 of a day. This is very noisy for reasons which I may or may not have time to explain. I assumed it was because the field was very crowded and we couldn't extract the brightnesses very, very accurately, but there may be something else. These are the velocity curves which tell you that it's radially pulsating. And BX also has got exactly the same shape as the other V652 Her when you get the O-C diagram, except this rate in this star is 20 times slower than V652 Her. So it's in a somewhat different part of the HI diagram doing much the same thing. And we've only just last week or the week before, I had a look at this stuff. I think there's a second order term there. I'm going to try and get some data here before we publish this stuff. This is, I had to show you that I think this picture is beautiful. It shows where all the pulsating stars are on an HR diagram. Here's the main sequence here. And an interesting thing about this diagram is that 4 of these groups of stars were discovered in South Africa, either at the Royal Observatory, which it was, no, it was already SAAO by then. At the SAAO, 4 of these groups of stars have been discovered there. This is a model by Simon Jeffrey and his collaborators. And he says, I don't think this star is post-asymptotic giant branch. I think what's happened is 2 evolved helium white dwarfs, that's stars that have got helium cores, they never got to burn helium, of about 1/3 of a solar mass, have actually been sitting around in a binary so long that they've merged. And if you merge these stars and form one star, it pushes them up here and then they start to cool off again. And that's where that star is on one of these loops. And this is fast evolution. This is caused by what they call late helium flashes, where you get very short bursts. The center of the star, as the star contracts, gets hot enough to trigger a very short burst of helium fusion. And the star does this kind of, it switches on and off and on and off and off and on. And then it eventually goes onto this cooling track again. And that is the end.
Dave, was such a beautiful talk. Any questions?